Have you ever aimed a laser pointer at a wall and watched that perfectly straight line of light illuminate your target? Light, as we know it, travels in a straight line. Or does it? Buckle up, because today we're going to explore a mind-bending phenomenon, how massive objects like the sun can actually bend light. This isn't some trick of the eye. It's a cornerstone of modern physics explained by Einstein's revolutionary theory of general relativity. Get ready to have your perception of gravity shattered as we delve into the strange and fascinating world of warped space-time. Imagine you have a smooth, taut sheet representing space-time, the fabric of the universe in which everything exists. Now picture placing a heavy bowling ball, representing the sun, on this sheet. What happens? The sheet dips and curves around the ball, right? That's exactly what massive objects do to space-time according to general relativity. Here's the key takeaway. Gravity isn't a pulling force like a magnet attracting metal. Instead, massive objects warp the very fabric of space-time. Picture it as a trampoline. The heavier you are, the more you sag and distort the surface. This warped space-time acts like a curved path, and even things with no mass like light can't resist following that curvature. This concept might seem radical, but it builds upon the work of earlier scientists like Isaac Newton. Newton's law of universal gravitation described gravity as a force between objects with mass, attracting them to each other proportionally to their masses and inversely proportional to the square of the distance between them. It was a powerful theory that explained planetary motion and celestial mechanics for centuries. However, as scientific observations became more precise, anomalies began to emerge. For instance, astronomers noticed slight discrepancies in the orbit of Mercury, the planet closest to the Sun. Newton's law couldn't fully account for these deviations. This paved the way for Einstein to propose a more comprehensive explanation of gravity. So how does this explain light bending around the Sun? Here's the magic. Light, despite having no mass, carries energy. In general relativity, E equals mc squared, where energy equals mass multiplied by the speed of light squared. Here, energy and mass are equivalent, and because of this energy, light interacts with the curvature of space-time. Think of it like this. Imagine a marble rolling on a perfectly flat surface. It would travel in a straight line. Now imagine that surface is warped, like a ramp. The marble wouldn't magically defy gravity and continue in a straight line, would it? It would follow the curve of the ramp. That's what light does when it encounters the warped space-time around a massive object. But how can something with no mass be affected by a theory based on mass and energy? Here's the key distinction. Light doesn't experience a force pulling it in. Instead, the curvature of space-time itself alters the path of the light wave. Imagine a car driving on a flat road. Now imagine that road slowly bends into a curve. The car doesn't experience a force pushing it to turn, it simply follows the curvature of the road itself. This analogy helps illustrate how light interacts with warped space-time. Einstein's famous equation, E equals mc squared, tells us that mass and energy are two sides of the same coin. They can be converted into one another under the right circumstances. Light, although massless, possesses energy. This energy, according to general relativity, contributes to the warping of space-time just like mass does. It's like adding another bowling ball, representing light's energy, to our analogy of the sheet. The more energy something has, the more it contributes to the curvature of space-time, and the more light will be bent as it travels nearby. This theory might seem mind-blowing, but there's actual proof. Back in 1919, a famous experiment during a solar eclipse confirmed Einstein's prediction. During a total eclipse, the sun's blinding light is temporarily blocked, allowing us to see stars that are normally hidden by the sun's glare. Here's the twist. According to general relativity, the sun's gravity should bend the light coming from these stars ever so slightly. This means their apparent position in the sky would be slightly shifted compared to if the sun wasn't there. And guess what? During the eclipse, astronomers led by Arthur Eddington observed exactly that. The stars appeared slightly out of place, confirming that the sun's gravity was indeed bending light. This was a major breakthrough and a huge validation of general relativity. It not only explained the previously observed anomalies in Mercury's orbit, but also opened up a whole new understanding of gravity and the universe. The concept of warped spacetime has far-reaching implications beyond light bending. Imagine a spaceship traveling near a massive object. Instead of feeling a pulling force, the spaceship would actually be following the curved path created by the object's gravity. It's like surfing a cosmic wave. The curvature of spacetime determines the trajectory of the spaceship, not some mysterious pulling force. This warped spacetime also explains phenomena like black holes. Black holes are incredibly dense objects with gravity so strong that not even light can escape their pull. The curvature of spacetime around a black hole is so extreme that it creates a point of no return, a one-way ticket to oblivion. Imagine our sheet analogy again. A bowling ball creates a dip, but a black hole would be like placing a massive object that rips a hole right through the sheet. The curvature becomes so severe that nothing can escape its grasp. General relativity isn't just a mind-bending theory, it has practical applications too. Take the Global Positioning System, GPS, for example. GPS relies on a network of satellites orbiting Earth that transmit very precise timing signals. However, Earth's gravity ever so slightly warps space-time around our planet. If not accounted for, this warping would cause inaccuracies in GPS calculations. Thankfully, by applying the principles of general relativity, scientists can adjust for this time dilation effect, ensuring your GPS provides accurate location data no matter where you are on Earth. There were initial debates and skepticism surrounding general relativity, particularly regarding its departure from Newtonian physics. However, numerous experiments and observations have confirmed its predictions. Today, general relativity is widely accepted as the most accurate theory of gravity. Einstein's light-bending prediction wasn't just a cool theory, it opened a window to a whole new way of observing the universe. This phenomenon, called gravitational lensing, acts like a natural magnifying glass in space. Massive objects like galaxies can bend light from even further away, allowing us to see faint or distant objects that would otherwise be invisible. It's like using the gravity of a giant cosmic lens to get a closer look at the universe's deepest secrets. Scientists are using gravitational lensing to peer back in time, study the distribution of matter in the universe, and even search for dark matter. So the next time you look up at the night sky, remember that the starlight you see might have taken a mind-bending journey, warped by gravity to reach your eyes. So, to recap, light doesn't bend because of some mysterious force pulling it. Instead, it follows the warped fabric of space-time created by massive objects. This revolutionary theory, general relativity, completely changed our understanding of gravity. It's not just a force, it's a consequence of how space-time itself is curved by mass and energy. The implications of this theory are vast, shaping our understanding of everything from the movement of planets to the formation of black holes. It's a testament to the power of human imagination and the ability of science to challenge our most basic assumptions about the universe. Mind blown. Thank you for joining us on this exploration of one of the universe's most important scientific concepts. If you've enjoyed this breakdown, be sure to like, share, and subscribe for more shattering content. Let us know what else you would like us to break down in the comments. Until next time, Earthlings, stay curious and keep exploring.